So we know how the TF reference frames get created and where they are defined based on the information we provide from the joint states topic and the robot_description parameter. Let's now see them in the context of our factory world. So we go to a new terminal, source our workspace setup files, and start our factory simulation. Now here we will do it slightly differently than what we did in week 4. Instead of seeing our factory world in Gazebo, let's use RViz like we did in week 2. Note that Gazebo will still be running in the background, but we will just not see the Gazebo GUI to visualize our factory. The reason to do this is that it is easier to see the TF frames and conceptually understand them in RViz. So recall from week 1 that launch files can be given arguments. We also did this in week 3 assignments. The hrwros_environment.launch file can take several arguments, but for this illustration we need 2 of them. First, we need an argument to say we don't want to start the Gazebo GUI. So we say GUI : false. And then we need another argument to say we want to start RViz instead of Gazebo. So we say RViz : true. And we launch the factory simulation by hitting enter. And we wait for a bit to have everything started up, and there we have it. Nice. So we now see only our 2 robot arms because the Turtlebot is not a part of our URDF or Zucro model. Note that the information regarding the different links and joints of the Turtlebot will still be published by Gazebo, and we can always visualize the Turtlebot in RViz by changing the robot description parameter inside the robot model display for the Turtlebot, like that. And we also notice that the Gazebo GUI has not started, which is what we wanted. Alright, so here on the left panel we see this unchecked element called TF. Let's check that box, and whoa, that's a lot of TF frames right there. It's natural, isn't it? We have so many links and joints in our factory. Okay, to make our life a little easier, let's actually enable only a few frames to understand the TF frames. To do so, let's first expand the TF element, and then under the frames element we can see the all enabled option is checked. So let's uncheck that. That's much better. And let's now zoom into the location of robot 2 and adjust our RViz view to a convenient perspective, like so. Now let's check the robot2_pedestal_link. Well, something happened because we see this green little thing popping out under the robot pedestal. So to really see it, let's go back to the left panel of RViz, to the robot model display for the 2 robot arms. This display element is responsible for rendering the different visual and collision geometries in our factory world. So if we scroll down here and uncheck the robot2_pedestal_link, remember this is what we are doing in the robot model display element. Then we can see the complete reference frame when we go back to the robot 2 position in RViz. Recall from the last video about how the location of the reference frames are decided based on the joints. So that's why we see this reference frame here, which is the joint between the world and the robot pedestal link. But these are fixed joints. So these reference frames will never move throughout the simulation. But in week 4, we learned how to use Move It commander to move our robots. So to visualize a moving TF frame in Arvis, let's go and select the vacuum underscore gripper2 underscore suction underscore cup frame in the TF display element. And then let's switch to a new terminal, source our setup files, and start Move It commander. Once it is ready, let's say we want to use robot 2, and then let's use the go command to move the robot 2 to R2 up position. Now before we hit enter, let's just resize the terminal a little bit so that we can also see the robot in Arvis, and focus on the vacuum gripper suction cup reference frame. And now we hit enter, and as the robot moves, you can see that the TF frame attached to the vacuum gripper suction cup of this robot arm is also moving with it. And this is actually an indication and confirmation that both the joint states information and robot description parameter are used to update reference frame information, because as the robot arm moves, its joint states get updated, and so does the reference frame information, which is associated with the end effector, which is in this case the vacuum gripper suction cup. This concludes the TF visualization illustration. See you in the next video.